I saw this news article on the NBC, I don't know, there was a link to an NBC News website that was talking about a superomniphobic material. And it just had so many buzzwords in there that I thought there must be some cool organic chemistry thing associated with this. Superomniphobic, right, I'm no Latin expert, but I can guess that that means it hates everything. And I can tell from these pictures here. So I went and looked up the paper that when you go read the original paper in the Journal of the American Chemical Society, it has much nicer pictures than they had on the news article. What you can see is here's 6 different liquids. They've put droplets on this material, completely different types of liquids in terms of chemical properties. And you can see this fabric that's been coated totally repels every one of these completely different types of liquids. Usually things that repel water don't repel oil or organic solvents and vice versa. And here they're actually, just to show that, oh, well, maybe you just set that little droplet down there really lightly. Maybe that's why it's not soaking in. So they took these streams or jets of these droplets and aimed them, and you can see they're just bouncing right off of this coated material. So it's pretty incredible that they're able to coat material. I'd like to have a raincoat made out of this, or not that I expect it to ever rain hexylamine or hexadecane from the skies, but that's pretty cool to have something that's that repellent. Maybe it means I won't stain my clothes anymore. Let's take a look at the molecules that are underlying this. This stuff was developed by Anish Tuteja's group at the University of Michigan, and he's a materials scientist. And what he did is he took this mesh and he coated that mesh with this very special mixture, sort of spray coated it with a very special mixture. And if you zoom in on this very tiny section where it's been spray coated, you can see that when the spray coating dried out, it left behind this very fine network of dried out material. And here's what he spray coated at the molecular level. If you could zoom down to the levels of atoms and bonds, you could see the material that he spray coated this with. And he says in the paper it's electrospun coating of cross-linked PDMS plus 50 weight % fluorodecyl POS on his state. So here's what all that stuff means. Polydimethylsiloxane is a very common polymer. So if you ever hear the people use the word silicone polymer, this is what silicone is. It's a bunch of silicon oxygen bonds in a framework, and there's alkyl groups hanging off of that. And it's generally very greasy. Usually it likes to attract organic solvents. So I would expect organic solvents to wet a material that's coated with siloxane polymers. But what he did is he mixed this polymer with these little nanocubes, and this is what POS means. It's a polyhedral oligomeric silsesquioxane. So a silsesquioxane, I'm not sure how long those have been around, 2 decades. They're tiny little nanocubes of siloxane polymer. So if you could imagine making a cube out of a siloxane polymer, you can see those same silicon oxygen bonds in there. But this particular one, dangling off the corners of each of the cubes, is a little piece of Teflon. So those perfluorinated alkanes, that's what Teflon is about. So he's got these little nanocubes of Teflon mixed in with greasy siloxane polymer, and when it dries out, physically, I mean, this is not purely a chemical issue. It forms these spaces that simply do not allow water droplets to push their way by them. The important point behind this is you can see that there's gaps in here. So in other words, this fabric or material is permeable to air, permeable to gases, permeable to water vapors, and yet it still repels droplets of many different types of liquids. And I think that's kind of a creative use of chemical properties, physical structure, to achieve some desired effect. So maybe someday you'll be able to wear raincoats that breathe better, and yet still can repel nerve gas agents or rain or whatever starts falling on you from the skies. Okay, so that's a very cool use of organic molecules with a little bit of inorganic silicon chemistry mixed in. Monday is a university holiday, and I want to remind you that on the first day of this class, I urged you to drive thy business. And so you have to make a decision what you're going to do with your Monday. You're exhausted, right? You've had exam after exam. I promise you, if you spend Monday morning doing organic chemistry, even though it's a university holiday, you will feel so good in the afternoon and so accomplished. Think how good you will feel if you have the courage to sit down on Monday morning and do some spectroscopy problems. So let me urge you to do that. Okay, so we are now starting on spectroscopy. We've spent a lot of time learning all kinds of new reactions. We're going to learn more, but we're going to take a break now and stop learning new reactions, and it's going to get rusty. It's up to you to keep practicing to keep your chemical reaction and mechanism skills strong. So we are... Oh, let me turn up the... I'm not sure I can easily speak louder, but I'll try to turn up the mic volume here. Okay, so we're going to start on spectroscopy. And I'm going to start off by, chapter 13 is about mass spectrometry and infrared spectrometry. And mass spectrometry is the kind of outlier. I'll try to quickly walk through this and explain to you why I won't ask you any mass spectrometry questions. So let's go ahead and start off. If you printed the sort of blank course notes online, this first page is basically filled in for you. There's nothing much for you to write. I just wanted to be able to talk about what is mass spectrometry. When you go into the airport, sometimes they'll grab people out of the line and swab them down and then use something very much like a mass spectrometer. It's not exactly the same, in order to measure whether you've got residue of explosives on you. And on the planet Mars right now, the rover Curiosity has a little probe that's digging and sniffing, and it's using a mass spectrometer to sniff for organic molecules. So let's talk about mass spectrometry and what it's good for. The idea behind a mass spectrometer is that you take a vanishingly small amount of sample. It takes next to nothing, amounts that are so small you can't even see them. And then you apply those at the entrance to a big instrument that heats up that sample and tries to waft it into the gas phase. So your sample molecules start to enter here, and then they hit this incredibly high voltage. And that high voltage will rip an electron. So if I have a zillion volts positive on this plate over here, on this little metal plate, it'll rip an electron out of your organic molecule. And then suddenly your organic molecule is missing an electron. It's now got a positive charge. And it will start freaking out and falling apart. It's got all this high energy. And if your molecule has a positive charge on it, you can now use a negatively charged plate right here. That's this blue thing. I guess I don't need to label it negative. You can see the negative charges here. The ions will get accelerated to that negatively charged plate. And you can make it so that they accelerate and move through this tiny little slit. And now all your fragments of your molecule that started to fall apart now move through this spectrometer and into a magnet. And the key is that in a magnetic field, ions are affected by the magnetic field. If I have a positive charge and I can see a negatively charged plate, I'm going to start moving towards that negatively charged plate. If I see a positively charged plate over here, it's going to repel me. So this magnet distorts the trajectories of these ions as they're moving quickly in this little stream. And ions that are very heavy, well, it's very hard to change their trajectory. They keep going almost straight and they bang into the magnet and don't go anywhere. Ions that are too light get too strongly attracted to the negatively charged part of the magnet, to the negative part of the field. And ions that have just the right mass will continue to move in just the right trajectory so they can be received by the detector. And so you can adjust the magnetic field and scan the strength of the magnetic field so that you can scan to see, are my ions light, are they medium-sized, or are they heavy? And that's a mass spectrum. And it is so sensitive, you can distinguish between ions that differ by a mass of 1 unit. That's the idea behind mass spectrometry. So a mass spectrum is really just a plot of all the little chunks of molecules that carry a positive charge. Okay, so you'll never run a mass spectrometry experiment in Chem 51 series. But let's take a look at a mass spectrum. So if you're at a rave this weekend, partying down, and somebody gives you a green tablet, and you bring it down to our mass spec facility over here in Reines Hall, and submit it for analysis, you'll get a mass spectrum that looks like this if you submit it for EI analysis. So here's what it looks like when you suck an electron. So here's ecstasy, MDMA. And if you suck an electron, it'll come out of the most nucleophilic, most energetic electrons. That's this lone pair. So it'll leave behind a positive charge right here after you suck an electron out of nitrogen. And then with all that high energy, this will start to fall apart. So your ecstasy ion that's missing an electron now has a positive charge. Bonds start popping apart. Here's a bond that cleaves, here's a bond that cleaves. And you'll see these fragments in your mass spectrum. And if you spend years studying these, you'll be able to just look at the fragments and guess what the original structure of the molecule is. So right here I've got the what's called the molecular ion. And I'll list that for you, molecular ion. We usually call this M+. If I just say M+, it means that's the molecular ion and the only thing missing is an electron. And you can see here it has a mass of 93, so you already have a pretty good guess. Yeah, that wasn't cut with some worthless anesthetic. That's the real deal they gave me. All this stuff over here, this debris, those are your fragments. And they all have a positive charge, otherwise they wouldn't have moved in the magnetic field. The fragmentation process gives plenty of neutral fragments as well, but you can't see those by mass spectrometry. So this fragmentation is both powerful because you can deduce chemical structure from that, but it's also very complex. It takes years of practicing to learn how to look at these fragmentation patterns and really make guesses as to what the original structure was. So I will never ask you to interpret a mass spectrum like this. I'll never ask you to look at the fragments and guess what was there. I think that those are important skills, but not at this stage. And I don't think any of the other sections in Chem 51C are asking you to interpret fragmentation patterns. So really the most useful thing is knowing that molecular formula. You can make some good guesses as to whether you've got the right stuff just by looking at the molecular formula, at the weight of that molecular ion, or the mass. Okay, so how typically is this used? So there's one very powerful thing you can do if you use high-resolution mass spectrometry. In other words, let's imagine that I have some peak in my mass spectrum right here. And instead of just saying that it has a mass of 30, I really measure accurately and determine that the mass is 30.1001054 down to the 5th decimal place. If I can measure accurately enough, I can distinguish between various ions that all have masses of 30. And so what I'll point out to you is that there's many different types of species that can have a mass of 30. Here's 3 possibilities right here, composed of carbon, hydrogen, oxygen, and nitrogen. So formaldehyde, CH2O, has a mass of 30.0106. But if I have 2 nitrogens and 2 hydrogens, that also has a mass of 30. It's just slightly different, but it is different. And if I take ethane gas, that also has a mass of 30, but it's not exactly the same as formaldehyde. In other words, these 3 different molecular formulas all have a slightly different mass if you measure it accurately enough. And so high-resolution mass spectrometry gives you a number that is so accurate that you can distinguish between various molecular formulae. In other words, if I give you the exact mass, you could go to a table and look up the molecular formula. Now, why does that work? It works because a proton has a different mass from a neutron. Right? They don't all have a mass of exactly 1. They're different out to about the 4th decimal place. And an oxygen atom has 8 protons and 8 neutrons in it. But if you look at the mass of carbon plus 4 hydrogens, it's similar. They're both about 16, but that's made up of 10 protons and 6 neutrons. And there's some electrons in there. So because a proton has a different mass from a neutron, that's what allows you to, if you measure accurately enough, to back out the molecular formula. So, hypothetically, on my exam, I could give you an exact mass, and then give you this big, huge table, and then you could look up the molecular formula in the table, and what a waste of your time that would be. So I'm not going to do that. Instead, I'm just going to give you the molecular formula, and we'll all just pretend that that came from mass spectrometry. I won't always give you a molecular formula, but if I do, you can assume we got that from mass spectrometry. So I won't ask you to look at mass spectra on my exams. I won't ask you to interpret exact masses. I'm just going to give you molecular formulae. And it's very easy to get those from mass spectrometry. Okay, that's our entire discussion of mass spectrometry. It's powerful stuff. But the way we use it most commonly nowadays is kind of at this level where it's giving us information that you don't need to interpret fragmentation patterns or look up molecular formulae in tables. That's not the way we're going to spend our time. So now let's switch on to, before I go beyond that, how are you going to, let's talk about how you will typically be using the molecular formula. So what would be a particular workflow or a problem where I give you a molecular formula? So here's a type of spectroscopy problem that you'll see on my problem sets, in discussion section, on the exams. A typical problem looks something like this, right? You don't see any mass spectrum there to worry you. What you do see is that I've given you a molecular formula, right? I've given you some chemical information. I've told you the starting materials. I've told you the reagent. I've told you the molecular formula of the product. And all you have to do is figure out what the structure of the product is. Now, the problem with this is you know a lot of reactions of HCl. And the problem is this some E1 elimination or some substitution reaction? The best thing that you could do is to take the molecular formula and start to use it, because it will give you some clues. If I give you a molecular formula, how do you use that information? Here's the way I would use it. I look over at my starting material here and I see, oh, there's 2 oxygens. Then I look at my molecular formula, well, there's only 1 oxygen, right? I have a pretty good idea about what kinds of things might have happened. It's, the 2 oxygens are not still there. The other thing that I don't see is a chlorine atom. So it's not going to be some SN1 or SN2 reaction because there's no chlorine in the molecular formula. You could all do this. This is very simple stuff, right? It's all based on a molecular formula that comes from mass spectrometry. I expect you to be able to look at this and say, oh, it lost an oxygen. Oh, there's no chlorine. See, that's easy stuff that I expect you to know how to do. The other thing that I expect you to know how to do is that I expect you to know that there's 1 degree of unsaturation in here. Right? You're now good at calculating degrees of unsaturation. And if there's 1 degree of unsaturation, that tells me that I've either formed a bond, a double bond, or a ring. So I now have powerful information about what kinds of structures I should be drawing out. So now it's up to you to just draw out some plausible structures that have 1 bond and 1 ring. Maybe I could pop this hydroxyl group off with acid and cyclize around. Right? I'm much quicker than you are right now at figuring out these possibilities. So that would be if this hydroxyl substituted that one. That only has 1 oxygen. Could be an E1 elimination reaction. Maybe I eliminated the tertiary alcohol to give a double bond. Maybe it was an SN1, but I've kind of already discounted that because obviously there's no chlorine in the molecular formula. I don't even need to think about that further. So anything where I've substituted with chlorine, I'm not even going to bother those out. So really, there's 2 structures here that match the molecular formula, and I would need some extra piece of information to figure out. It's kind of clear from looking at the molecular formula that I lost a hydroxy group, probably the tertiary one, and then something happened. And so now on the bottom of this problem here, I've given you an IR spectrum. In other words, you need 1 extra piece of information to help figure this out. Yes?
How did you know there was 1 degree of unsaturation?
From the molecular formula, you can back that out. You guys should know how to calculate degrees of unsaturation from molecular formula. Yeah, we covered that. It's like we cover it and then we don't use it and we forget about it. So there's a set of rules that I gave you for molecular formula-based degrees of unsaturation. Okay, so you don't know how to look at IR spectra yet. And so I'll show you how to look at this IR spectra, and in a fraction of an instant, you will have decided which of these 2 products here, between these 2 products here, which of those are the products that you get in this reaction. Okay, so let's talk about spectroscopy in general, and then we'll home in and we'll spend the rest of the lecture talking about infrared spectroscopy. This is an infrared spectrum on the bottom of this page. And maybe I'll just tell you right now what the structure is so you're not left guessing. Okay. So let's talk about spectroscopy as a general process here. Spectroscopy means absorbing some type of electromagnetic radiation and looking what happens to the molecule. So there's 3 types of spectroscopy that we will cover. Mass spectrometry is not spectroscopy. Mass spectrometry is not absorbing light. Mass spectrometry is ionizing molecules and literally destroying them. Whereas having molecules absorb light doesn't destroy molecules. So mass spectrometry is completely different from spectroscopy. But spectroscopy means you absorb some type of light, and we'll talk about 3 types, and each one has its own chapter. So UV visible spectroscopy, you should have used that in Chem 1. Beer's law, absorption of visible light, and you would measure some extinction coefficient. You could calculate the concentrations. By looking at the wavelength at which things absorb, you can make guesses about the structure of organic molecules. And so typically what you're looking at with UV light is you're causing electrons to move farther away from the nucleus. So electrons, and the tech term for that would be that they move to higher energy orbitals. But the bottom line is that electrons move farther from the nucleus. And we're going to cover that in chapter 16. We'll talk about UV visible spectroscopy and how chemical structure correlates with features that you see in the UV visible spectrum. Okay, in this chapter, chapter 13, we're going to talk about infrared spectroscopy. And mainly what's happening when you absorb an infrared photon is that bonds start to vibrate. I mean, there's other kinds of actions. They can do scissoring kinds of actions. But the main thing that we're going to be concerned with infrared spectroscopy is that when you absorb an infrared photon, if it's just the right wavelength, your bonds will start to vibrate. And you can look at those absorptions and figure out something about the structure of the molecule. So that's chapter 13. And then in chapter 14, in NMR, we're going to be using radio waves, or radio frequency waves. And here what we're simply doing is we're flipping up nuclear spins. That's supposed to be nuclear spin. We're flipping nuclear spins up or down with radio waves. So visible photons pack a lot of energy. If you can get an organic molecule to absorb an ultraviolet photon or a visible photon, you can get them to do some very crazy reactions. Infrared is not energetic enough to cause chemical reactions to occur. You just make bonds vibrate, and that's heat. Things get hot. So if you go to a fast food restaurant, oftentimes they have French fries sitting under an IR lamp. They're just using infrared light to make the bonds vibrate so that the food stays hot. And then nuclear magnetic resonance, you may be someday running MRIs. NMR and magnetic resonance imaging are basically based on the same technique. Okay, so let's go ahead and talk about infrared. That's this chapter. So next chapter will be NMR, and then we'll have to wait to chapter 16 to get to UV visible spectroscopy. Okay, so let's go back and return. I already gave you a peek at an IR spectrum. And I'm going to talk about 3 reasons why the IR spectrum looks really dumb and crazy. And there's all kinds of reasons why they do it this way, but in retrospect, all those reasons are now 50 years old and dumb. Okay, so first of all, I hope it's totally obvious to you, the IR spectra are upside down, right? I'm going to refer to peaks in the IR spectrum, but the peaks go downward, they don't go up. I mean, really, I ought to call them valleys. So you have to understand when I use the term peak that I'm talking about an absorption, and when you're absorbing light, you see sort of a valley instead of a peak. So IR spectroscopists, for whatever reason, decided to turn their spectrum upside down. The reason they did that is they're really plotting transmission of light. In other words, the light that can pass through a solution. And transmission is the opposite of absorption. So they were like UV vis spectroscopists who plot how much light passes through, but we're really going to be interested in absorption here, not the transmission, not how much light shines through your sample, but how much light is absorbed by a sample. And so absorption goes downward. And so when I talk about an absorption, I'm talking about things that go down. Okay, so that's one weird feature. The other is IR spectra seem flipped around. In other words, normally when I plot out a UV vis spectrum, you start at low wavelength over here, and you go to higher and higher wavelength over here on the right-hand side. But look at the axis here, the x-axis. It gets smaller and smaller and smaller as you go to the right-hand side. The big numbers are over here on the start, and then as you walk across, it gets smaller and smaller. So that seems weird. At least it should seem weird to you. So we plot IR spectra in terms of decreasing bond vibration frequency. And so I'm going to talk about frequency, but what they've actually done here, the reason why the axis looks like that, is they've actually plotted in terms of wavelength. So if you were to use units of wavelength, then this axis would be increasing that way. And you're going to have to do some kind of basic, if you wanted, if you really wanted to, well, let me just make the point that the units here aren't even your normal units of frequency. And I'm going to keep talking about bond vibration and frequency. But these units here are units called inverse centimeters. Now, I don't know about you, but I'm used to hearing about frequency in terms of hertz per second, 60 times per second, 100,000 cycles per second. FM radio stations are measured in per second, and that's not a unit of time. If you really want to convert this into hertz frequency, you can use this little equation that frequency equals the speed of light divided by wavelength, and you can convert directly these inverse centimeters back into a frequency, but nobody does that. So I'll keep talking about frequency, but I'll give you frequency in units of inverse wave numbers. Just seems really odd, and you've got to get used to that. I'll say frequency, but I'm going to give you inverse wave numbers. Everybody, that's the way the IR spectroscopy works. Okay, so this is an IR spectrum of THC. So next time you're out smoking a joint, this is the stuff that's getting you high. What do I see in here? I see some CH stretches. We'll talk about this. I see an OH stretch. Maybe there's some stuff here from the benzene ring, those CC double bonds, and a lot of useless junk. So I'll show you how to interpret an IR spectrum when you see it. Of course, if you had shown me that, I could not have told you that that was delta 9 tetrahydrocannabinol, but I could have pointed out the gross features of that molecule by looking at that IR spectrum. Okay, so let's talk about what is it that causes those absorptions at the level of bonds and atoms. What is it that's making a molecule either absorb or not absorb in the IR spectrum? And this is, it's the basic laws of physics. So there's this Hooke's laws for springs that tells you that the vibration frequency depends on some kind of a force constant for the spring. Stiff springs vibrate very quickly. Floppy springs vibrate very slowly. And it also depends on the masses you're pulling. If I have two super heavy masses, they don't move very quickly. Heavy things don't move quickly. Light things can move quickly when they're attached to a spring. So if I think about how two balls or two atoms should respond when they're attached by a springy bond, it depends on the bond stiffness and it depends on the mass that I'm pulling. So if I have this big huge mass and this teeny tiny little mass held by a spring, that spring can drag that tiny mass back and forth very easily. Right? A tiny mass is easy to move. You expect a very fast vibration frequency if you're just dragging a tiny little mass around. I hope that makes sense. So small atoms like hydrogen should vibrate very quickly. They're small. Heavy atoms like carbon, it takes time for them to move back and forth. Okay, so just two carbon-carbon bond ought to be like your average everyday bond, vibrating back and forth. If I put a double bond between two carbon atoms, now I've got two springs there. It's harder. The spring action will be stiffer. So if it's stiffer, you'd expect it to return back to its original position more quickly. In other words, it'll more quickly vibrate back to its original position. Okay, you don't need to really think about springs when you're looking at IR spectra. I'm going to tell you about some of the regions of the IR spectra, and I'll expect you to memorize these regions. But they all can be explained based on Hooke's law. Okay, so first, there's this region, so I'm going to talk about wave numbers now. Here on this bottom axis, I'm going to refer to wave numbers. So in this region here, usually above about 3,000, but it starts at about 2,500 as a demarcation line. This is where I have all the bonds to H. So in other words, bonds between C and H. Remember, H is this tiny little light atom. Very high frequency, very easy to move that hydrogen atom. Nitrogen to H, oxygen to H. So bonds to H, and of course we're never going to take the IR spectrum of hydrogen gas, so you're never going to have two light atoms stuck to each other. Okay, so all the bonds to H appear past 2,500 wave numbers. There's this kind of place in the IR spectrum where you very rarely see things, and this is where triple bonds appear between 2,000 and 2,500 wave numbers. Actually, triple bonds are not that common, even though we had an entire chapter on triple bonds. I've got a CC triple bond there, and I've got an NC triple bond here. And I guess if you had carbon monoxide in there, you might, but you don't, we're not going to analyze that. Now, if we have one fewer pi bond, instead of triple bonds, just double bonds, it doesn't vibrate as we go from triple to double to single bonds, we see lower and lower frequencies, slower and slower vibrations. So here's CC double bonds, NC double bonds, and oxygen C double bonds. Carbonyls are the most prominent part of that region of the spectrum. You'll also notice there's a difference between the mass of carbon, nitrogen, and oxygen. I'm kind of staggering this a little bit. A carbonyl, oxygen is heavier than carbon, so you should expect that the frequency for a carbonyl should be a little bit higher than for a CC double bond. And there's another feature that's different as well. Now, out over here below 1500 wave numbers, that's all the single bonds. Halogens attached to single bonds, carbon-carbon bonds, nitrogen-carbon bonds, oxygen-carbon bonds. This is referred to as the fingerprint region. It's very complex. And there's all kinds of other vibration modes that are in here, like stuff like this, which is not exactly a vibration, or coupled modes, where two springs actually vibrate in a coupled or concerted fashion. And I'll give you one piece of advice that I'm going to follow, I hope you do, and that is just to ignore this region. Look, everything has CC bonds. You're not going to learn anything by looking in that region. Just ignore it. If I show you a spectrum and it's got all this mess in here, just put your hand over it, right? It's that easy. There, you're done interpreting that region. So really, you just look at this other half of the spectrum and you get information about, oh, do we have OH bonds or triple bonds or double bonds? That's what you should be getting out of IR. All this other stuff that you might be tempted to use this other region for, I promise you will be easier by using NMR. Okay, so let's now take a look. Let's go back and look at some spectra. Now that we know these regions of the IR spectrum, it'll be very exciting to see if we can make heads or tails out of a spectrum. Not sure why I have two different. Okay, so here's an IR spectrum of a molecule, and let's just see if we can match the features of this molecule up to peaks. Again, the peaks are upside down, to these upside down peaks in the IR spectrum. So here's my molecule. What do I see here in my molecule? Well, I've got a cyano group. There's a triple bond, and look at that. There's an absorption at 2230 wave numbers. That's that triple bond. That's the CN triple bond doing this stuff, vibrating back and forth. I see some other stuff here from 3070 to 2870 wave numbers. All those things right there, that's these CHs vibrating. And we'll talk about this, but I can actually distinguish the CHs from the methyl from the CHs on the benzene ring. I expect those to have a different vibration frequency, and they do. I can see them here in this IR spectrum. I see this peak around 1610, which looks unusually intense to me. And I'm kind of surprised that it's so intense, but that's the pi bonds related to this arene ring. Now, how can you get a chance to look at some molecules and see if you can identify features? On our website, there's a resources link, and on that resources tab on the class website, there's a link to something called the SDBS database, Spectral Database System. It's a Japanese website that has 50,000 IR spectra for you to practice with. You can just type in a molecular formula, C4H8O, and you'll instantly come up with 50 IR spectra that you could look at. And just look at them one at a time and say, oh, I see the carbonyl stretch. Oh, I see the triple bond. Oh, I see the CHs. Nothing will train you to interpret IR spectra or NMR spectra better than looking at IR spectra and NMR spectra. If you take a class in surfing and you never bother to use the surfboard out on the waves, I promise you, you will fail the surfing exam, right? You have to practice this stuff. And the only way to practice is by looking at many different spectra. And I can't stand here in lecture and show you enough spectra. So it's worth you taking a look at. And it's easy to do. And so again, out here in the single bond region, there's nothing, just avert your eyes. You don't need to see any of that stuff. I promise you that will be easier to interpret by looking at C13 spectroscopy. Okay, so not all bonds, not all stretches are equally intense. And so let's talk about what is it that makes some peaks really intense and some peaks kind of small and hard to see. And the single most important feature that makes an IR absorption intense is bond polarity. In fact, that's exactly what makes it possible to detect an IR signal. Is the polarity of a bond. So that's a fundamental requirement, that bonds must be polar in order for you to see them in IR spectroscopy. So let's look at these three types of triple bonds up on top here. So I've got a cyano group where a carbon is attached to electronegative nitrogen. And over here I have a terminal acetylene or a terminal alkyne where there's, on one side of the alkyne there's an R group and on the other side there's an H. R is not the same as H. Doesn't have the same electronegativity. Carbon doesn't have the same electronegativity as H. So that bond is a little bit polar. But if I take an alkyne that is exactly symmetrically substituted, you can't excite this very simple bond vibration if it's perfectly symmetrical because there is zero dipole moment. You have to have a dipole moment. In other words, a difference in electronegativity between these two atoms in order for you to excite a transition. So if the two R groups are even slightly different, you can sometimes see a barely perceptible peak, but I would never bother looking for that. So what you expect is the most intense triple bonds will come from cyano groups, whereas simple alkynes should not be as intense. And so let's take a look at two very similar triple bonded molecules. This is a molecule called benzonitrile. It's a benzene ring with a cyano group sticking off of it. And down below I've got almost the same molecule. And the only difference is that the triple bond is a CC triple bond. And if we look at the intensities of that triple bond peak in here, you can see that I've got it labeled here. So here in this around 2000 to 2500, that's where my triple bonds are. So here's the cyano group triple bond. Look how intense that is. Wow, goes almost all the way to absorbing all the light. And here's the CC triple bond. I mean, that's almost in the noise there. You kind of have to squint to see that, that triple bond there between the two carbons. So here's the CC triple bond right there, and here's that CN triple bond that's so polar. So bond polarity affects the intensity of peaks. Now there's one, yes, question. How do I know that this peak here is the triple bond? Because the only thing that appears down here from 2000 to 2500 is triple bonds. And I memorized that. And you need to memorize that. So that goes back to this issue of regions of the IR. So the question is, how do I know that that peak is the triple bond? Remember I told you that this region from 2000 to 2500 wave numbers, that's where triple bonds show. And I've looked at a lot of IR spectra to make me confident in that assignment. Now there's one other feature of this IR spectra that I'll talk about shortly, and that is, look at this huge difference. Everything else looks kind of similar in these spectra, but what's this about? Turns out that that's the CH at the end of this triple bond. Very distinctive. All the other CHs on the benzene ring are here, but the CH at the end of that triple bond, we'll talk about that in a moment. Look how intense that is. A single CH bond is way more intense than all these other CHs put together. Yes?
Can you explain why CH bonds or any bond of H's towards the left of triple or double bonds?
So why do CH bonds have such high frequencies? Because it's very easy to move an H atom. So they vibrate very quickly. Whereas if I had a cannonball attached to my hand, it would move very slowly. Something light, the spring can move very quickly. Something that's heavy, it's just hard to move.
Does that mean a triple bond is easier to move than double?
Triple bonds are stiff. But stiff means that it returns back to its original position very quickly because the spring is so stiff. Whereas if I had some springy spring, it would very slowly return to the original position. But you don't even need to know Hooke's law. You can just remember those regions of the IR spectrum is what you really ought to be doing, and practicing by looking at spectra. Okay, so bond polarity matters a lot in terms of intensity. Okay, so let's talk about bond polarity and hydrogen bonding. They're kind of related. So here's three types of bonds to hydrogen atoms: OH bonds, NH bonds, and CH bonds. And of these, OH bonds are more polar, they are also better at hydrogen bonding. OH bonds are better at hydrogen bonding than NH bonds, and OH bonds are better at way better at hydrogen bonding than a CH bond, which you typically assume doesn't hydrogen bond. So because the bond is more polar, the OH bond is more intense than an NH bond. And an OH bond is way, way, way more intense than a CH bond. Usually a single OH bond in your molecule is more intense than all the other CHs added together. So typically, when I see a big lump like this, and the technical term for this is a big ass lump. When I see that in my spectrum, there is no question in my mind that there is either a hydroxyl group or a carboxylic acid in my molecule. Now, if it's sort of medium, so I guess it could be a bunch of NHs, but even an NH, which usually gives a big lump, isn't as big as this. Look how big that is. I mean, it's stretching all the way down to 100% absorbance. So this is a molecule, this is an IR spectrum of ethanol. Ethanol has 5 CHs. Here's those 5 CH stretches. And that one OH is bigger than all of those other CHs combined. So the OH bond has this, it's so powerful at absorbing. And the effect of hydrogen bonding, because there's so many different ways that I can orient myself to hydrogen bond with this, it broadens this peak out. You're actually seeing lots of little different versions of that OH bond where it's hydrogen bonded in different ways. That's why the peak is so broad. So hydroxyl groups, carboxylic acids, there is an unmistakable dominant peak between 3,000 and 4,000 wave numbers. And so I hope that when you see that kind of peak that you're readily able to recognize that, look at that, I must have an OH in my molecule. And let me see if I can find that spectrum of the tetrahydrocannabinol, because I'll direct your attention to that. When I looked at that, it was hard for me to mistake the fact that, oh my gosh, there must be an OH in this molecule. Do you see that big lump there between 3,000 and 4,000 wave numbers? Right? You're capable of interpreting that in an IR spectrum, so I expect you to be able to recognize when they're alcohols. NHs can also give big lumps too. And you'll have to look at some spectra for amine NHs versus OHs in order to give yourself a sense for how much bigger the OHs are in the IR spectrum. Okay, so there's one extra thing we can get past 3,000 for bonds connected to H. Whenever I get an IR spectra, it's not as though all CHs are the same. CHs are different. The CHs attached to the end of a triple bond like this are stiffer than the CHs attached to sp2 carbons. So this carbon right here is sp hybridized. These carbons here on the benzene ring are sp2 hybridized. And these carbons over here on the alkane part are sp3 hybridized. And the more S character, 50% S character, the stiffer that bond is. So as a result, this bond here, so the generalization is that protons attached to the end of an alkyne, like this one right here, have the highest frequency. And then if you're attached to an alkene, you've got the next highest frequency. And then if you're just attached to an alkane, you're at not quite as high a frequency. So that's these stretches over here. So there's this correlation between H attached to alkyne, H attached to alkene, and H attached to alkane as to how high a frequency you have. And this one attached to the alkyne is so distinctive. It's way over here at 3,300 wave numbers. The protons attached to alkenes are usually kind of close to 3,000. They're usually kind of close to the sp3 hybridized. So that's these right here. And then all these other CHs attached to the alkanes are over here. And usually there's a lot of those. Okay, there's one thing I want you to do whenever you see CH stretches, and that's to draw a line at 3,000 wave numbers. And so let me draw that line. I usually physically draw the line, right? I usually just, I mean, you may not watch this. I'll just take a piece of paper and I'll draw a line here at 3,000. You can see how easy this is. That line is very powerful. Because when I look on the right-hand side of this line, that's where all my sp3 hybridized CHs appear. Ethyl, methyl, butyl, cyclohexyl. All the singly bonded carbons that have H's on them, those stretches appear on the right-hand side at lower frequency than 3000. All the H's that are attached to double bonds or benzene rings, those appear slightly above or above 3000 wave numbers. You can instantly get some information about whether you have H's attached to alkenes simply by looking to see if you have CH stretches above 3000 wave numbers. And of course, H attached to an alkyne is usually this spearhead spike that's sticking out on its own at 3300 wave numbers. So that's impossible to miss because it's usually so intense. Okay, so draw that line at 3000. It'll help you to see whether you've got H's attached to alkenes. Let me remind you, not all alkenes have H's on them. So, okay, so you now know everything that I know about interpreting IR spectroscopy. Maybe I have one or two more gimmicks, but you just don't need to know those. So let's take a look at a couple of spectra, and we'll just practice here. We'll just see how good you are at interpreting IR spectra. Okay, I've got two molecules written on the top here. This top molecule has 1, 2, 3, 4, 5, 6 carbons. It's hexane. And this other molecule, I think, is hexanol. Okay, I've got two spectra there. Which one is hexane and which one is hexanol? Yeah, the bottom one is hexane. Come on. That doesn't take any difficulty to see. Let me just, in case you missed it here. Oh, look at that. That's so easy to see. I don't even need to look at the top spectrum. I'm done. But we could look at let's look at the top spectrum because I can't resist. Right? If I drew that line at 3000 wave numbers, see how satisfying it is that all those CHs are lower than 3000 wave numbers? Just in case I thought there might be a CC double bond in there, I'm now sure there's not. And over here, I draw that line at 3000. Ah, how nice. All the CH stretches are below 3000 wave numbers. Okay, so see how easy it is to use IR spectroscopy? That's so easy. And I just ignored all this stuff below 1500 that's just totally worthless for us. Okay, let's practice again. Okay, this is not a good one because once again, it's so easy. I've made it too easy for you. These two molecules have the same molecular formula. You couldn't use mass spectrometry to distinguish these because they have exactly the same molecular formula. You'd have to use something like IR spectroscopy. So if I gave you the mass spec, you might be, gee, I don't know. But when I show you the IR, it's absolutely clear which of these is the alcohol. But what's even clearer to me is which one is the ketone. I don't even have to look at the bottom spectra. If I never showed you the bottom spectrum, so I hope you can all see here, there's this huge peak, this broadened peak at 3480. That's the OH on the alcohol. So that's the OH peak. So this bottom spectrum is the alcohol. But I didn't need to look at the bottom spectra because there's an equally distinctive peak for me. And that is that this carbonyl group, because it's polar, carbonyls absorb very strongly. That's going to be one of the principal uses for IR spectroscopy for you. And so let me darken that IR peak for the carbonyl. Because it's polar, it's very strong. CC double bonds don't absorb that strongly. They're not polar, but carbonyls absorb super strongly. They're usually as distinctive as these OH stretches in the spectrum. Let's take another look at this alcohol. See that little tiny blip here at 3083? That's above 3000 wave numbers. That confirms for me that there's H's attached to alkenes in this alcohol molecule. And when I come over here to this other ketone molecule where I can see the carbonyl, I don't see anything past 3000 wave numbers. It's all CH's attached to single bonded carbons. So there's all, oftentimes you can figure it out just by seeing one diagnostic peak in the IR, but there's usually lots of extra peaks that can help you have information and interpret that. Okay, I have one last set of spectra here for you to interpret. Okay, I have an amide, an amide, and I have this cyanoalcohol thing. Now it's a little crazier. I've got this lumpy peak here, but I also got this lumpy mess over here. There's lumpy mess, and I look at my molecules. Oh, there's this carboxamide with two NHs on here. That's probably leading to a lumpy mess. And this one has a hydroxyl. That's got a lumpy mess. So now which is which? Which one is the cyano compound? There's the cyanostretch. 2260, that's the triple bonded region from 2000 to 2500 wave numbers. So here is my cyanostretch right there. And when I come over here and I see these stretches around 1700, that's the carbonyl. That's the CO stretches. And don't worry about the second peak at 1610. So you can see here, this gives you a chance to see what the NH stretches look like over here in this blobby NH mess. And here's the OH business for my alcohol. So the cyanoalcohol is on top. There's the cyano group, there's the OH group. And then this carboxamide over here has this not quite as blobby NH stretch, and then the big time carbonyl over there. Okay, so there's problems in the back of the chapter. That's it. We're done with IR, and you're now experts. You just need to practice. Go practice looking at lots of spectra. Go to the SDBS database and look at lots of spectra and practice.